it's a pleasure to guide you through this session this morning, and well, it's a even greater pleasure for me to introduce our first keynote speaker. Actually, it's Sebastian Uhlemann. I need my notes to don't mix up the numbers here and the years. So, well, Sebastian studied a joint Master of Applied Geophysics at Aachen, Zurich, and Delft, and then he went in 2012 to the British Geological Survey, where he focused on geophysical monitoring for early warning of landslides. He received his PhD from the ETH Zurich then in 2018. From 2018 to 2022, he worked first as a postdoc and then later as a research scientist at the Lawrence Berkeley National Lab in California. And there he was intensively involved doing near-surface geophysics for mapping hydrological processes related to climate change in Arctic and alpine environments. In 2022, he also received the Near-Surface Geophysics Early Career Achievement Award from AGU. And then, well, he came back to Europe, and now, or since 2024, he's now a professor of environmental geophysics of University of Bremen and can now join the European critical zone community again. So it's a pleasure. Welcome, Sebastian.
Thank you very much. I didn't think that you would be so prepared. That's so much. Anyways, yeah, thank you very much for having me. And yeah, it's also a pleasure to open this day today. And yeah, so what I'm going to talk about now is basically integrated geophysical sensing. So if you think of geophysics, usually what geophysicists do, and I'm a geophysicist, you measure some sort of parameters that are usually only important to geophysicists, but don't really matter to anyone else, like hydrologists or eco-hydrologists. And to get there, to get to some parameters that we actually want to know as critical zone scientists, we have different ways we can do that. And what I'm going to show you today is how we can use geophysics combined with a lot of different sensors and hydrological modeling to basically map groundwater flow dynamics in a hill slope. So I'm going to talk a little bit about hill slope hydrology, because that's what the study site is. And we can see a very simplified sketch of a mountainous watershed here. So you have this mountainous watershed, and in this watershed you have your hill slopes, you have your floodplains, and you have river corridors. But let's just focus on the hill slopes. And I would argue that the hill slopes are quite important, because no matter where you are in this mountainous watersheds, whether you're in alpine conditions or montane conditions, you will have some sort of water input from the surface. So it could be snowmelt or it could be just rain, which will go through the soil, the weathered bedrock and the bedrock, and at some point will end up again in your stream. And while it's doing that, so while it's moving through basically your subsurface, so while the water is moving through a subsurface, it will actually take and lose some nutrients, some carbon, some metals, and it will also, depending on the parameters that you have in the subsurface, it will basically define which sort of base flow conditions you have or how much recharge you get into the streams. So really what we want to understand here is how watersheds retain, release water, nutrients, carbon, and metals over kind of short time frames, but also over long time frames. And I think for that, to really get that, we have to understand the bedrock. So we have to understand the bedrock characteristics, but also groundwater flow in the bedrock. And what I'm going to show you today is stuff that I did while I was in Berkeley and afterwards too, which is related to a project that is called Watershed Function Science Focus Area. So it's a project that is funded by the US Department of Energy, and basically funds about 100 scientists or so at Berkeley Lab that try and look at the entire system. So going from the hill slopes over the floodplains to the river corridors to really understand how climate change will impact these mountainous watersheds. So the study site itself is in the central Rocky Mountains. It's the East River watershed. Has an area of about 300 square kilometers, average elevation of 3,260 meters or so, and a topographic relief of 1,400 meters. So you still, even within this high watershed, you have very strong gradients in hydrology, but also in life zone. So we're really going from alpine environments to montane environments. And the East River itself is actually, quite important because it's a headwater of the Colorado River. And the Colorado River, as you probably know, is kind of the lifeline of the western United States because it supplies water to about 40 million people and 20,000 square kilometers of agricultural land. The East River watershed is also what you call a community watershed. So it's full of different sort of sensors and research, and a lot of people do research within this watershed. If we just look at a little video here, what we see in blue and red is geophysical data. That's airborne electromagnetic data, so it was acquired with a helicopter, and it basically shows you the subsurface electrical resistivity, where blue here indicates mostly Mancos shale-dominated lithology, and red, for instance, are some granitic intrusions that you have. And in general, you see a lot of different things too. There are like some limestones and sandstones on this side, but in general, there's a lot of data that tells us something about the subsurface geology, let's say. And in this talk, I'm going to focus on this area here. So this area is Mount Snodgrass. And basically what you see here in blue, this is the Mancos Shale. And then in red, we have a granitic intrusion. It's quartz monzonite porphyry. And here we really were interested in understanding how the water is flowing down this hill over the granitic intrusion down into the Mancos Shale dimming. So this is what it looks like from an bird's eye view. So you have basically here canopy height. So we have also a lot of remote sensing data. So high resolution LiDAR data, but also hyperspectral data. So we actually know which plant types we have. In this case, we have some conifer trees. They're up to 20 meters tall. And they are mostly in this side of the area. So in white here, that's our monitoring transect. And here, we have all these conifer trees. What's a bit difficult to see, perhaps, is a dashed line here. That's the interface between colluvium and the quartz monzonite porphyry as you would find it in a geological map. So on the granitic intrusion, we have a lot of conifer trees, and then when we go to the colluvium or Mancos shale-dominated domain, we're in this meadow. And then over here, so on the right-hand side, we have a little stream. This is what it looks like in a cross-section and having a geophysics behind it. So we see again that we have the high resistivities here for the granitic intrusion. So that's kind of pretty low porosity bedrock. And then we have the colluvium in kind of this greenish colors. That's mostly landslide-derived material. And then we have Mancos shale, which is a shale, so relatively low resistivities. Then, as I mentioned, what we are measuring here is just the resistivity, right? So I'm going to show you changes in resistivity, but we want to try and relate them to hydrological dynamics. And to do that, we need some additional data. So in our case, we have 6 locations where we're measuring soil moisture at up to 6 different depths. We measure soil temperature, we measure air temperature, we measure snow thickness. We also have a deep borehole, so that's about 20 meters deep or so. In this borehole, we're having a groundwater level logger, so we're measuring groundwater EC, temperature, and water table. And then we have 4 additional shallow piezometers that are also measuring water table. And in addition, we also have a pretty high resolution weather station. So in one of these boreholes, so this about 25 meter deep borehole, we also acquired what we call NMR data, so nuclear magnetic resonance. This actually gives us some idea about the water content that we have in the subsurface around the borehole, as well as the hydraulic conductivities. And it's not only giving us the water content, we also can actually distinguish between, for instance, clay-bound water, capillary-bound water, and free water. And what you see from that, together with the geological interpretation, is that we actually seem to have a lot of free water in the Mancos shale, and we also have high electrolyte conductivity, which is somewhat counterintuitive because we're going into bedrock. But in this case, because we are so close to this intrusion, the bedrock is actually highly fractured, and so we have a large amount of free water and a high hydraulic conductivity. So what we're going to do is we're looking at changes in resistivity in a second. And these changes in resistivity, if we correct for the effects of temperature, and we assume that the pore water conductivity is relatively constant, or is constant, then we are basically left with changes in moisture content. And at this site, everything here was basically connected to some network, and we always had the data in near real time, although that's not really important now. So this is just some of the data that we gather. So that's mostly the data from the weather station. So we have, quite a bit of rainfall, a lot of snow during the winter. So that's about 1.5 meters thick snowpack that then melts relatively quickly. Here you can see the temperature. Here an estimate of the daily evapotranspiration. And then down here we have the data from the borehole. So what you see is basically that over the winter there's hardly any input to the system, as it seems, because the water is just so the water table is slowly declining. Then as soon as we get into the snowmelt period, we have a very strong peak, which is then followed by a second peak, which we don't really know what the origin is coming from at this point, because, well, it doesn't seem to relate to rainfall at least. Well, if we look at the temperature, we see that clearly temperature, this is the orange line, is going down with this first peak by, almost half a degree or so. So this seems to be snowmelt related. And in the second one, we also see a decrease again. So maybe that's snowmelt that's coming from further higher, that's coming from higher up in the watershed. Just because, we have a bit of time and we're talking about sensors. This is a sensor that we use to measure subsurface temperature as well as air temperature. And it's a sensor that we developed at Berkeley Lab. Is low power, so it runs off 2 AA batteries, and it runs off two AA batteries for about 3 years. It's relatively low cost, and it's actually high resolution. So what we have here is basically temperature sensors every 5 to 10 centimeters that have an accuracy of about 0.015 degrees. So pretty high resolution. And the reason it is so high is because we developed it to put it into permafrost environments where you really want to know with very high accuracy what the temperatures are. And in addition to that, we can also measure the deformation of the probe, even though that's not important for this example. But if we put MEMS accelerometers on this probe, we can actually see how this probe is deforming over time, and as well with relatively high accuracy. So what we get from this data is basically something that looks like that. So we get temperature in the air, and we get temperature down in the subsurface. So here you see temperatures up to about, 1.20 meters or so, and then, so 1.20 meters or so in the air, and then about 50 centimeters at depth. And then we can use this data, and in particular the vertical gradient, to estimate the snow thickness. So when the vertical gradient has a peak, this means that one sensor is in the air, and one sensor is in the snow, so we can actually get a relatively good estimate of the snow thickness. And when you compare it to a nearby reference station, which is the purple line here, you can also see that our estimate is actually pretty good, and it's capturing all the dynamics. But rather than just having one station in a 50 kilometer or so radius, in this case we had 6 stations just along our transect, so we got a good idea about snow thickness. So now what I'm going to show you is some of the geophysical results. So it's basically a little video that goes through the monitoring data. So it's just one measurement at basically lunchtime every day, and we see that we're looking at a snowmelt event. So snowmelt is going down, and then, or the snow thickness is going down, and then the only thing we have are some rainfall events, but we actually won't focus on them. Then we see the resistivity and the change in resistivity. And because it's a bit small, I made it bigger. So what we can see here first, when we don't have any snowmelt, is that the subsurface is pretty constant, but then as soon as we get snowmelt, we see a pretty nice infiltration front. So we saw that the resistivity was decreasing from the surface and was then basically going down. And then later on, what we see too is basically an upwelling of groundwater. So here we see the groundwater level in the borehole. And once the groundwater is upwelling, we will also see a subhorizontal feature that's appearing here, which is basically now. And then the water is streaming into, or is basically being released into the stream that's over here. So down here, relatively homogeneous. Now, if we look at the upper part where we have the fractured bedrock and we look at the snowmelt, it looks very different. So we see that the result, or the data is very heterogeneous, and we see strong changes, especially below tree locations. So the locations that you see here as tree are actually the locations where there are trees in the field. And you can see that there are strong changes, especially here, there, and also around this tree. So what we get from that is basically, we get an understanding of how the system evolves, or what the dynamics of the system are. So we can see that we have relatively homogeneous infiltration, let's say, down in this lower part of the slope, and we have very heterogeneous conditions in the upper part of the slope. But it's mostly what we get from this data. The other thing that we can look at is actually more high-resolution results. And this is shown here. So here what I show is just moisture content at one of those moisture content sites doing snowmelt. And what you see are these little peaks here. So they're daily peaks. And we can see that doing snowmelt, we have a little phase difference. So the shallow sensors, they react first, and then the deep sensors, which is the red line, reacts last. And we can also see this from the resistivity data. So down here is the resistivity data. We also see that we can kind of see an infiltration front that comes from the surface to the lower layers. Now what's interesting here too is when we look at this period. So here the red sensor, the deepest sensor, responds first, then green, orange, and blue. So we're going basically from 80 centimeters to 10 centimeters. And that's basically upwelling. The other thing that we can look at is just what happens in summer. So in summer, we actually have quite a bit of rainfall. I mean, if you see it's not a lot of rainfall. It's like 10, 15 millimeters a day or so. But still, there's quite a bit of rainfall. But the system itself seems to dry out because we see mostly increase in resistivity over time, except of this location here where we get some upwelling. This is actually also interesting. So where we get this upwelling is where we have veratrum, so a plant that needs a lot of water, a lot of nutrients, and is actually only growing in this area here. She's very interested. So what we get from the resistivity data is just some dynamics that we can see, but we don't really see what the actual flow conditions are. So to get to the stage, what we thought we could do is we just run a hydrological model. In this case, we're running a P-flowtran model, and the boundary conditions are defined basically by the stream down here and by the effective rainfall, so rainfall minus evapotranspiration that we can apply to this boundary here. Then if we use a very simple parameterization of the model, so we just have two layers, soil and bedrock, then what we see is mostly just a vertical infiltration into the subsurface. So this doesn't really explain what we see in the field. If we make it a little bit more complex, then we actually take the geology. So we include the interface between the granodiorite and the Mancos shale. We see something that is already more what we see in the resistivity data. So we see this homogeneous infiltration down here, and we see some more heterogeneous flow pathways down here. So what I'm showing is basically just some ray tracing, right? So everything here is some ray tracing data or ray tracing results. So then if we make it even more complex and we actually take the geophysical data and we use some petrophysical relationships that we can basically establish from some of the boreholes that we have at the site, we can use the resistivity data to derive some estimates of permeability and porosity and then run the model with that. And what we can see is something that is very similar to what we get from the monitoring data. So we see very strong dynamics down here, so mostly vertical flow down to the water table. We see rapid lateral flow over here. And then at the tree locations, we see that water is actually infiltrating into the bedrock. And yeah, I have it summarized there. Okay. So, but basically what we can see here is that, yeah, we get this infiltration to the bedrock, and this might actually be quite important, right? Because if you think that in these watersheds, or in general, due to climate change, we will have a change in kind of precipitation patterns with, long drought conditions or more, extreme rainfall events. Then if we have this deep flow, especially around the tree locations, that could actually recharge the, let's say, deep aquifer or rock moisture, then these trees might actually be more resilient to drought conditions because they will have this water that is further down in the bedrock during times of prolonged droughts, which is something that we already saw in the talk yesterday, right? So this is basically all I want to show. And really what I want to highlight here is that, when we combine geophysical monitoring, with a lot of different sensor data and hydrological modeling, we can actually get a good understanding of what's happening in the subsurface. So we get an understanding of the dynamics that we have in the subsurface. And in this case, we see how the different bedrock units behave differently. We see how potentially the trees have a very strong impact on recharge in the system. But in general, we see a lot of dynamics. What I didn't really go into detail here, there's also, of course, some methodological developments. We have a lot of data that we actually need to process. And as I mentioned at the beginning, the resistivity is actually sensitive to variations in temperature. And in this case, where we have a change in slope angle, we have a change in aspect, and so on, we actually have very different temperature conditions in the subsurface, so we had to correct for those. And just as an outlook, what we're doing at the moment is actually we're looking at how different forest management strategies are changing the hydrology at the site. So we have a new study site now where next year they're going to do some cutting down of trees as forest management, and this probably has a strong impact on the subsurface hydrology, and that's something that we're trying to understand now. And yeah, thank you very much, and thank you very much again for having me.